When we talk about the definite integral of a function, we are visually looking at the area under the curve between two bounds, a and b. But what if we want to find the integral from b to infinity? Or maybe negative infinity to b? Or even crazier, negative infinity to positive infinity? Wait, this sounds absurd. Shouldn't an area over an infinite amount of space just be infinite? If that's the case, why are we even looking at this type of problem? I promise all of these questions are going to be answered in this video. Starting off with the first question, suppose I have the function f of x is equal to 1 over x to the fourth. Let's start off with something simple, evaluating the definite integral of this function. For now, let's have some constant value a be the bottom bound and b be the top bound. For the sake of this example, let's say a equals 1 and b is just some positive number greater than 1. So our expression for the area is the integral from 1 to b of 1 over x to the fourth times dx. Now let's actually evaluate this. The first step to evaluating a definite integral is to find an antiderivative of the function, or in this case, 1 over x to the fourth. Meaning we need a function such that when differentiated equals 1 over x to the fourth. With some elementary integration, we find that the antiderivative of this function is negative 1 over 3 times x to the third. Now we simply use the second fundamental theorem of calculus and evaluate the antiderivative with the top bound and subtract from it the antiderivative evaluated at the bottom bound. So the area under the curve of this function at these bounds 1 and b is negative 1 over 3 times b cubed plus 1/3. Right now we don't have an exact value for b. It's still some arbitrary number. But let's see what happens when we let b get larger and larger. As we increase the value of b, we cover more area under the curve, meaning our integral expression gets larger and larger. As b gets larger, the area gets larger, the value of the expression gets larger. So what would happen if we let b equal infinity? Actually, let me clarify that. What would this integral expression evaluate to if b tends toward infinity? As in, what is the value of the limit as b goes to infinity of this expression? Did you see the trick? Instead of letting b equal infinity, because frankly we can't do that, a number can't equal infinity, we observe what happens to the integral as b goes toward infinity. Now we can actually evaluate this limit. We can separate this expression using the limit law of addition. And now let's start with the left limit. Allow me to show you the graph of negative 1 over 3 times b cubed. You see, as b gets larger and larger, the value of our expression gets closer and closer to 0, since the denominator grows at a faster rate than the numerator. So the limit of this part of the function as b approaches infinity is going to go to 0. The limit of b approaching infinity of 1/3 is simply 1/3 because the 1/3 doesn't change regardless of whether or not b is approaching infinity or not. In the end, all we are left with is the 1/3. So it turns out this integral expression, the area under the curve as b goes to infinity, is exactly 1/3. What we have just seen is the area of a region bounded by infinite length being finite. Now that we went through an example showing how we can intuitively unpack the meaning of an integral at infinity, we can now formalize this idea. The formula for an integral of any function with the top bound being infinity, is the limit as b approaches infinity of the integral from a to b of f of x dx. Here, a is any real number of our choice. It does not change. And b is a sort of a dummy variable. We don't care about the actual value of b, just as we did in our example. All we care about is what does this value approach as b goes to infinity. In order to find our area under the curve, we first evaluate the definite integral of this function with a constant bound and an arbitrary bound. Then we take the limit as the arbitrary bound goes to infinity. If, say, you want to find the area from negative infinity to a point, then you set the top bound constant, in this case a real number b, and set the bottom bound as a dummy variable a, and take the limit as a goes to negative infinity. So that answers our first two questions. Now, what do we do if we want to evaluate the integral from negative infinity to positive infinity? Before we used one dummy variable and took its limit. Now we have to use two dummy variables and take their respective limits. Let me show you what I mean. Let's start definite. Suppose I now have three variables, a, b, and c, where c is between a and b. Let's set c as the constant number. I want to know what the area under the curve is from negative infinity to positive infinity, so I can combine the ideas from the first two examples. Let's divide this area into two separate parts. The first part is from a to c, or the left side of the expression. The second part is from c to b, or the right side of the expression. Let's work on the left portion first. If I let a go to negative infinity, my integral expression for this portion becomes the limit as a goes to negative infinity of the integral from a to c, since that's the top bound of this left part, of my function times dx. Again, this is exactly what we did before, and this covers the area under the curve from negative infinity up to a constant value c. Now for the right side. Going from c to b, we want to know the value of our expression as b approaches positive infinity. So this part is going to be the limit as b goes to positive infinity of the integral from c to b of f of x times dx. This is going to cover my area from the constant value c up to positive infinity. We have the expressions for the left side of the area and the right side of the area. So the total area under the curve is going to be the sum of these two expressions. Thus, the limit from negative infinity to positive infinity of f of x dx is equal to the limit as a approaches negative infinity of the integral from a to c of f of x dx plus the limit as b goes to positive infinity of the integral from c to b of f of x dx. Now, I really want to emphasize three things. 1. C is not some specific value. You can choose c to be any real number, as long as it's just between your other two bounds, a and b, and the expression would still apply. We just need c as a sort of mediator to allow us to deal with the problem piecewise. 2. We are not seeing what happens when these dummy variables, a and b, equal infinity. Instead, we're observing what happens as they approach infinity. Limits and equalities are very different things. And 3, not all of these expressions are finite. For example, the integral from 1 to infinity of 1 over x dx is in fact infinity. It does not converge to a finite value. Only specific examples converge to a finite result. By the way, these type of integrals are called improper integrals. There's a lot more to go into about this topic, but I'll leave it here for now. As always, strive to know why something works. Not just that, it does. With that being said, I'll see you guys in the next one.